Hello, welcome to the next video lecture on strength of materials.
One of the important definition is called torsional rigidity. It is a torque required to produce an unit angle of twist in unit length of the shaft. That is the definition of torsional rigidity or torsional stiffness. So TR is equal to T by theta. T is torque and theta is angle of twist. But from torsion equation, we know that T by J is equal to G theta by L. So theta is actually TL by GJ. When I substitute theta into T by theta equation, I will get T by theta is equal to Gj by L. So torsional rigidity or torsional stiffness is equal to Gj per unit length of the shaft. When L is equal to 1, it becomes Gj. So T by theta is equal to Gj per unit length of the shaft. And the reciprocal of this torsional stiffness or torsional rigidity is called torsional flexibility. One more parameter that is important is torsional strength. Normally, we compare different shafts in terms of torsional stiffness or torsional strength. Torsional strength is also called as efficiency of the shaft. The definition of torsional strength is the torque required to induce unit maximum shear stress. So it is T by tau. If you compare this with torsional stiffness is T by theta and torsional strength is T by tau. Ts stands for torsional strength here. So Ts is equal to T by tau. And from torsion equation, T by tau is nothing but J by R. So J by R I have written. But J by R is nothing but the polar section modulus, Zp. So I can write Ts is equal to T by tau is equal to Zp. So torsional strength is equivalent to polar section modulus of the shaft. Next, we will talk about design of shafts. In most of the components that are required for mechanical engineering applications or any system, we come across rotating and power transmitting members which are called as shafts. So designing means obtaining the dimensions of the shaft, normally the diameter of the shaft, and designing the suitable material of the shaft. That is called design of shafts. Based on the power that has to be transmitted, availability of the material, cost of the material, etc., a shaft is designed. So basically, shaft design means finding the diameter of the shaft. In order to design the shaft, we have two approaches. One is called design based on the strength. Strength here, nothing but torsional strength. According to this theory or criterion, the maximum shear stress induced on the outer surface of the shaft, tau, should not exceed the permissible value. According to this theorem, tau should not exceed a permissible value. That is called strength criterion. And the other one is called rigidity criterion or design based on rigidity. Rigidity is nothing but stiffness. This is another way in which we can design the shaft. According to this theory or criterion, diameter of the shaft is calculated based on the given value of angle of twist. So theta should not exceed a permissible value. Okay, this is called design based on rigidity. Just observe here, T by J is equal to tau by R is equal to G theta by L. This is the torsion equation. Now, if I consider this one, this region, this is strength criterion. This part of the torsion equation is called strength criterion. And if I consider this portion, this is rigidity criterion. So strength criterion is nothing but T by J is equal to tau by R. And rigidity criterion is nothing but T by J is equal to T theta by L. So these two criterion you should know, because depending on the requirement, whether you are trying to limit the shear stress induced in the shaft or you are trying to limit the permissible angle of twist in the shaft, you can design the shaft in these two ways. But sometimes you may have to satisfy both the criterion. In that case, you will have to combine these two criterions. One more important thing is, if we know the power transmitted, I can calculate what is torque. So power transmitted P is equal to 2 pi nt divided by 60. This will be in watts. This is mean torque. Normally it will be in Newton meter. This N is speed of the shaft in RPM, and this P is power transmitted. This equation is known to you. If I use only 60, it becomes watt. If I use 60,000 here, it becomes kilowatt. This equation also may be required for our calculations. With this much knowledge, we can try to solve some of the problems related to shaft design. Read this problem. A solid shaft is subjected to a maximum torque of 25 kilonewton meter. Determine a suitable diameter if allowable shear stress and the twist are limited to 80 Newton per mm square and 1 degree respectively for a length of 20 times the diameter of the shaft. Take G is equal to 80 gigapascal. So let us try to list the given parameters first. Maximum torque 25 kilonewton meter. So I will call it as T max. It is 25 kilonewton meter. It is actually 25 into 10 power 6 Newton millimeter. Kilo is 10 power 3. Again, from meter to millimeter, when I convert, another 10 power 3 will come. So totally it becomes 25 into 10 power 6 Newton millimeter. Limiting value of shear stress is given. So tau is 80 Newton per millimeter square. This is the maximum shear stress the shaft can experience. And limiting value of angle of twist is also given. So theta is limited to 1 degree. It is given in terms of degree, but we have to use it in radians in the equation. So when we convert it into radians, it becomes pi by 180 radian. And length of 20 times the diameter of the shaft. So L is equal to 20 times the diameter. And G is given as 80 gigapascal. If I write this in terms of Newton per mm square, it becomes 80 into 10 power 3 Newton per millimeter square. Both tau and theta are given here. Means we have to use both strength criterion and rigidity criterion. So let us use strength criterion first. Based on strength criterion, we know that T by J is equal to tau by R. T is what? 25 into 10 power 6 divided by J is, for solid shaft, it will be pi d to the power 4 by 32. This is J is equal to tau. Limiting value of tau is given. It is 80 Newton per mm square. And R is nothing but d by 2, diameter by 2. So now you observe in this equation, only d is unknown. Okay, you will get some value for d cube, and you take the cube root of that, you will get the value of d. So if you solve this, you will get 116.75 mm. So this should be the diameter of the shaft based on strength criterion. Let us use rigidity criterion now. Based on, we know that T by J is equal to G theta by L. Again, we will substitute all the values. T is 25 into 10 power 6 divided by J is pi d to the power 4 by 32 is equal to G is 80 into 10 power 3 into theta in radians, pi divided by 180 divided by L. L is given in terms of D, so we'll substitute 20 into D here. So again, you see, now it is the equation in terms of d cube or d power 4 by d. Right? We can solve it. We can get d cube first, and we can take the cube root of that, and we can find out what is d. So d from this criterion, you will get 153.93 mm. So we have two answers now. Which one should be finalized as the diameter of the shaft? See, let d is equal to 116.75 mm. And this is the answer what I got from strength criterion. And I'll use this diameter and try to find out what is the theta I get for this diameter. Now I'm using d is equal to 116.75. I'm trying to find out what is theta. So what will be theta here? Theta is equal to T L by Gj. Based on the torsion equation, T by J is equal to G theta by L. So theta should be equal to T L by Gj. So let us try to find out this. T is what? 25 into 10 power 6. And L is what? It is 20d divided by 20 into d. Again, d I know. D I'll, in place of d, I'll substitute 116.75. And G is 80 into 10 power 3. And J is pi into d power 4 divided by 32. This you calculate, you will get it in radians. If you multiply that with 180 by pi, you will get in degrees. I am getting 0.04 radian. And if I multiply it 180 and divide by pi, I will get 2.29 degree. Now you see, if I finalize diameter as 116.75 mm, my theta is going beyond 1 degree, which is not allowed. According to the condition, maximum theta is 1 degree. It should not go beyond that. So if I choose 116.75 as diameter of the shaft, it cannot sustain the angle of twist. In terms of rigidity, it fails. We have to go for the maximum diameter. So you always remember, use both criterion, find out the diameters, whichever is maximum, that you have to finalize. Now, if I take 153.93, obviously my theta value will fall less than 1 degree. So it satisfies rigidity criterion also. So this is greater than 1 degree, which is not allowed. Therefore, diameter of the shaft should be 153.93 mm. This is the minimum diameter. Any value more than this can be chosen as diameter, but that diameter shaft may not be available in the market. See, these shafts are available in standard sizes. Maybe next standard available is 154 mm or 160 mm. So whichever is closer to this, but more than this, that will be chosen as a final design value. That's how shaft design is done. If you want, you can write approximately 154 mm. Like this, you can round off and write. So we'll go to next problem. A hollow shaft having internal diameter 40% of its external diameter. It transmits 562.5 kilowatt power at 100 rpm. Determine the inner and outer diameters if the shear stress is not to exceed 60 Newton per mm square, and the twist in a length of 2.5 meter should not exceed 1.3 degree. The maximum torque is 25% greater than the mean torque. Take rigidity modulus as 9 into 10 power 4 Newton per mm square. So as we did in the previous case, let us try to list the given data. See, it's a hollow shaft now. Previously, problem was on solid shaft. Now it's a hollow shaft. He says internal diameter is 40% of the external diameter. Means DI is equal to 0.4 times DO. Inner diameter is 40% of the external diameter, means it is 0.4 into D naught. That relation is given. Power that has to be transmitted is given P 562.5 kilowatt, and speed is given N is rotating at 100 rpm, and maximum shear stress is limited to 60 Newton per mm square, and angle of twist is limited to 1.3 degree, 1.3 degree, or it is 1.3 into pi divided by 180 radian. And he says it is in a length of 2.5 meters. So L is 2.5 meter, which is 2500 mm. That's the length of the shaft. And the last sentence you see, maximum torque is 25% greater than the mean torque. So T max is equal to 25% greater than the mean torque. So it should be 1.25 times the mean torque. See, this you should be careful. I have seen students making a big mistake here. They will just try to take T max is equal to 0.25 T mean, which is not correct. How? If you want to understand, I will give an example. Let us say you have 100 rupees. Someone gives you some more cash and it becomes 25% more than what you have. Means how much it becomes? It becomes 125 rupees. 25% more than what you had means you had 100 rupees. 25% more means 25 rupees will be added. So 125 rupees. So T max is 1.25 times T mean. G is equal to 9 into 10 power 4 Newton per mm square. That's given. First thing is we have to find out what is the maximum torque that the shaft should transmit. See, whenever P and N are given, you can easily find out what is the torque required. P, I know that it is 2 pi NT divided by 60. Since power is given in kilowatt, I will take it as 1000 here, 60,000. But remember, this P here is nothing but mean torque. It is not the maximum torque. Always power from the shaft is evaluated based on the mean torque, not from the maximum torque. P is 562.5 kilowatt. That should be equal to 2 pi into N. N is 100 here. Into T, we don't know. Let us keep it as unknown. Divided by 60,000. So now you can evaluate T from this. T, we will obtain it as 53714.8 Newton meter. Remember, you will obtain it in Newton meter, not millimeter, because power is in watt. Watt is joule per second and joule is Newton meter. So you will get torque in Newton meter only here. But you have to use it in Newton millimeter. Let us convert this. So convert this as 53.7148 into 10 power 6 Newton millimeter. Because I'm converting meter to millimeter, so there 10 power 3 will come. And I'm shifting the decimal point after 53, so another 10 power 3. So totally it becomes 10 power 6. This is the T mean. But a shaft is not normally designed for mean torque. It should be designed for the maximum torque. What happens if I design for the mean torque? It may not withstand the maximum torque. So always it should be designed for the maximum torque. And according to the problem data, he says maximum torque is 1.25 times the mean torque. So let us calculate maximum torque. Maximum torque is 1.25 into 53.7148 into 10 power 6. It comes out to be 67.1435 into 10 power 6 Newton millimeter. This is the torque the shaft should be capable of transmitting. Now, based on this torque, let us try to find out what is the diameter required. We have two criteria. First criterion is strength criterion. So first one, based on strength criterion, we know that T by J is equal to tau by R. And remember, it is a hollow shaft now. So R is actually R naught. And J is pi into D naught power 4 minus Di power 4 divided by 32. Let us try to substitute all the given value here. In place of T, we have to use maximum torque, which is 67.1435 into 10 power 6 divided by J is pi into D naught power 4 minus Di power 4 divided by 32. Both D naught and Di both are unknown here, so I will keep it as it is. And that should be equal to tau. Tau is 60 divided by R naught. R naught is D naught by 2. I will write it as 67.1435 into 10 power 6 into D naught by 2 is equal to 60 into pi divided by 32 into, see, D naught power 4, I will take it outside. So it becomes 1 minus Di power 4 divided by D naught power 4. Now, one of the D naught can be cancelled with the D naught of the left hand side. So it becomes an equation in terms of D naught cube. Di by D naught, if you take, it is 0.4 here. It's given in the problem. So you substitute this and find out what is D naught from this. So you will get D naught as 180.2 mm. And from this you can find out Di also. We will do that later. Now take up rigidity criterion. Based on rigidity criterion, T by J is equal to d theta by L. So T here is 67.1435 into 10 power 6 divided by J is, again I will write the same thing, D naught power 4 minus Di power 4 divided by 32 is equal to G. G is 9 into 10 power 4 theta. Theta is 1.3 pi divided by 180, that is theta, divided by L. L is given as 2500 mm. So in this equation, D naught power 4, you can take it outside. In the bracket, it becomes 1 minus Di power 4 by D naught power 4, and Di by D naught is 0.4. So 0.4 power 4 it becomes. So you can easily calculate what is D naught here. So do that calculation. When you do that, D naught, you will get it as 171.2 mm. Therefore, I will write it as DO should be equal to 180.2 mm. And Di, you take 0.4 into D naught and calculate what it is. It comes out to be 72.08 mm. So this should be the cross section of the shaft. This is the final answer. We'll go to one more problem. Determine the maximum torque that can be applied to a shaft of 300 mm diameter. The permissible angle of twist is 1.5 degree in a length of 5 meter, and the shear stress is not to exceed 42 Newton per mm square. Take G is equal to 84 GPa. You have to do the reverse. Here diameter is given. You have to find out what is the maximum torque that it can safely transmit. So let us try to list the given parameters first. It's a solid shaft, 300 mm is the diameter, and limiting value for theta is 1.5 degree, which is 1.5 pi by 180 radian. Length is 5 meter, which is 5000 mm. Tau, limiting value for shear stress is 42 Newton per mm square, and rigidity modulus G is 84 GPa, which is 84 into 10 power 3 Newton per mm square. This much is given to you. We have to find out the torque that can be safely transmitted through this shaft. Both tau and theta are given. So when tau and theta both are given as limiting values, you have to use both criterion. So let us use strength criterion first. Based on strength criterion, T by J is equal to tau by R. T is not known, we have to find out T. J is pi into 300 power 4 divided by 32, and tau is 42 divided by R is d by 2, so 300 by 2. So here I can find out what is the T. T, if you calculate, you will get 222.66 into 10 power 6 Newton millimeter. So based on the strength criterion, the safe torque that can be transmitted is 222.66 in 10 power 6 Newton millimeter. We will see based on rigidity criterion. Rigidity criterion says T by J is equal to T theta by L. So when I substitute all the values except T, T is unknown here. Pi into 300 power 4 divided by 32 is equal to G is 84 into 10 power B into theta is 1.5 pi by 180 divided by L is 5000. So find out what is T from this. T is 349.754 into 10 power 6 Newton millimeter. Now again we have two values. See, for diameters we have taken maximum value because we want the shaft to be safer in both the criteria. It is not the diameter now, it's a load. Torque is nothing but the load on the shaft. If I take 349.754 as the torque that can be transmitted through the shaft, the tau will exceed 42. Tau should not exceed 42. So you have to go for the minimum value. When it is load, you have to choose a minimum of the two what you get. When it is dimension, like diameter, you have to choose a maximum. You have to be very clear in this. Since it is a load, the safe load that can be transmitted through the shaft based on strength criterion is 222. A safe torque that can be transmitted through the shaft in rigidity criterion is 349. So overall, the maximum torque that can be transmitted safely is 222 only, not 349. So you write safe torque that can be transmitted is 222.66 into 10 power 6 Newton millimeter, or it is 222.66 kilo Newton meter. And I will give you two more problems for homework. Determine the diameter of the solid shaft which will transmit 440 kilowatt at 250 rpm. If maximum torsional shear stress is to be limited to 40 Newton per mm square, take G is equal to 84 gigapascal. Here you see this G value, whatever is given in the problem, it is not at all required because it is not limiting the theta. Only if the limiting value theta is given, then only that G is required. Otherwise, it's not required. Fully strength criterion you have to use, and final answer you have to calculate. Answer is, answer you should get 124 mm. So D should be 124. And fifth problem, you see, what length is required for a solid shaft of 12 mm diameter so that the cross section at one end can be rotated 90 degree with respect to the other end without exceeding the allowable shear stress of 70 megapascal in the shaft. Observe that here limiting values are given for shear stress as well as theta, and length you have to find out. I just think the same set of equation, we are not using any other equation. Just see how you combine these two criterion and find out the length. The answer you should get is 10.771 meter. This is the answer you should get.